Alrighty then. Well, it's a terrible clap. Terrible, but we're going to continue anyway. All right, everybody. This is episode number 8. I think that's, yes, 8. My monastery life. Why? Because this is going to be the final episode because I plan on starting traveling back to the East Coast and hopefully maybe visit upon different folks that may or may not be around and stuff. It's, hey, all I know is you meet people on the internet, and for some reason, even after they get to know you as Matt or other assigned names or whatever, they still usually call you memes. Why? They both begin with M. I know, I know. Imagine my shock. All right, narcissistic superlatives aside, what are we talking about today? So, as folks start to roll in, I am going to be committing a lot of blasphemy in all different forms today. So, you've been warned. Okay, unless you join later, then you haven't been warned, unless you're actually going through the replay. But we're going to be talking about a model that is it partially trollish? Yes. But physicists have a long history of trolling. I feel they are some of the best trolls, or at least maybe I'm overly attributing that to Professor Feynman. Um, but basically, we're calling it Lambda-OCDM. Okay. Because we have our standard Lambda-CDM. What is that? All right. Lambda, there's some dark energy. Maybe it's a cosmological constant or something. And then we have cold, dark matter. All right. The only difference, and I'm really going to postulate here, is there is old, cool, dark matter. Now, why do I say cool? Because cool can, one, include cold. And to be fair, you can extend that out there. But also, it's like, what do we mostly see? There's a bunch of stuff far away. Oh, we see some stars and stuff. Why? Because they're hot. If it isn't hot, it's kind of a lot harder to see. Then we're gonna need to see a shadow from some maybe protoplanet or other planet there. That kind of sounds like some fairly cool matter. Maybe it's not really, really cold. Maybe it's around Earth, so it's like I don't know, like 270. It was about 300 Kelvin normally. Because was it 293? Oh no, 0 is the freezing point of water. Okay, so yeah, no, about 293 Kelvin. Yeah, because it's on the board. Okay. Now, if I got that wrong, I apologize. But all right, so what is the whole claim? All right, we still have basically most of the model as we know it. All we're doing is providing, we're conjecturing, if you would, we may be able to explain some other phenomena without necessarily having to introduce new particles. Now, I'm not saying that there aren't axions or anyons or any different on out there. That may be totally the case. Something about having 17 elementary particles. It also happens to be the number of wallpaper tilings you can have, and I believe the 2 dimensions or general geometry type things. At least that's what it says on Wikipedia. First heard that from Dad. Um, and I have wallpaper groups. I think something like that. Um, but okay, so how are we going to do this? Number one, we're postulating it's old. Why? Probably been there for a while. My personal opinion, I know stunning and brave. I'm saying the cosmos as we know it, probably greater than 14 billion years. Could be totally wrong. I just think the technical term is it's ginormous, perhaps gimungulous. I'm not sure which is a greater form of either there. All right. So we have ginormous, vast expanse. All right. We have a whiteboard here. We have some markers. We can do marking type things. Let's see if this one's better. Well, all right. I like that one. It's nice and dark. All right. We're going to have a vast system. Okay. Now assume your standard Big Bang cosmology or something. We have a vast, vast cosmos. Okay. Vast, vast cosmos. Imagine ginormous spherical type thing. Okay. Ginormous spherical type thing here. All right. So what happens if we're number orders of magnitude? Because right now, to our observation, we put our little Earth in here because we're a happy little planet here. Yes, I drew a little smiley face in there. All right, we're at Earth. Going out to our cosmic horizon. All right. Seems to take about 13. What it actually is, the radius is what Wolfram Alpha's for, because it's one of those weird things. It's not necessarily what you think it is. Uh, let's see what we got. Okay, so radius of observable universe. All right, what we got? Okay, so the radius of the observable universe. I was totally off. Yes, we say it's because we're factoring in expansion and all that jazz, whatever it is. All right, so 46.5 billion years. All right, so I was off by like a factor of three. 46.5 big B light years. All right. So 46.5 billion light years. Okay. That's pretty ginormous. Now, is it like 20 quadrillion light years? No, because that's basically of the order of magnitude approximately that we're at least conjecturing. Why are we conjecturing that? Because, all right, so here's the claim. The general claim is, all right, we have certain constants in nature. We have what, as we know, and again, maybe it's totally wrong, minimal units for time, space. Basically, you get the Planck time. You've got the Planck length. These are minimums to our calculations of elementary units. Now, Professor Wolfram would conjecture with some of the folks at the Wolfram Physics Project that we might have ins, maybe an elementary unit of space is our 10 to the minus 100 or something like that. It kind of lines up with the Planck volume a little bit. But I'm just saying that it's very interesting because he feels like there's underlying computation going on there. Now, that that sounds like it might be the case. There may be other reasons, but we don't need to speculate upon speculation here. We're going to just do our base speculation. Okay. So those are minimums. What if they were maximums? What the heck do I mean by this? We go to our friend, Wolfram Alpha, where I just asked it a question and it gave me an answer because that's one of the things we were talking about a little bit earlier. It's like, all right, back in the day, we had certain experiments. You need to follow these journals, get the most up to date experiments, and then you need to go around and perhaps solve different things. And then probably resolving something that somebody else already did because we didn't have an archive or Google to search these things. We didn't have Wolfram Alpha. So it's very exciting that we actually live in a time and place where we can literally have access to the sum total of humanity, often not paywalled, like in Wolfram Alpha here. It's a free website. Yeah, I have the premium thing because Steam Wolfram doesn't have a Patreon or something. So I actually use some of the tools. And the extra computation time every once in a while, it's fun. Okay. So what the heck are we saying here? Length. How do you do an inverse of a Planck length? What if we did something like this? Meters squared over the Planck length. What the heck does that do? Then the meter squared, so we'll get an actual meter component out. We're basically just doing 1 over that, except if we do squared, we get an extra dimension. Oh, oh, yeah, Wolfram Alpha has been, I think it's getting a lot of computational pings from our large language model friends. Okay. The meters, wait a second, means this meter squared you're doing over the Planck length? Weren't you doing this the other day with kilograms? Yes, I was, my friends, because again, Thad, John Williamson, and Rick DeWitt have all stressed often very important to look at things and their inverses. Just like Professor Carroll was the one who's like, yeah, within physics, a lot of times we do a calculation. If that doesn't really make sense, you square it, cube it, take the square root. You play around and see what happens. And you try to have an actual physical interpretation. Because if you're getting half dimensions and stuff, does that always make sense? I don't know. I ain't smart enough for that. But I digress. What happens when we do our meters squared over the Planck length? We get this here. This is a ginormous number. How do you even say that? 6.187 times 10 to the 34 meters. That's basically the claim of the radius of the observable universe. All right. The 46 billion. All right. So that would be, all right. So that's like 46, and then billion is 9 zeros. Okay. So that'd be like 46 times 0.5 times 10 to the 9. Okay. This is 6.187 times 10 to the 34 meters. Well, that number seems to be quite a bit larger than that one. 25 orders of magnitude, but apparently when we incorporate the different stuff and things, it gives you something like this. All right. So basically 7 orders of magnitude of the diameter. All right, so they're kind of already doubling that. That's a pretty ginormous number. So what are we talking about? We're talking about we're probably like 7 or 8 orders of magnitude larger than a lot of the things out there that we believe we can see within the observable universe. All right. So okay, we don't need to math all that away that much. But what's the other part here? The other part here is what we're trying to figure out is okay. Take the smiley face. Assume it isn't necessarily Earth anymore. What if it was the center of whatever? Okay. Why am I saying the center of whatever? Oh, everything's all right. So the claim is that ultimately, what do we have going on? All right. We're going to claim an N hypersphere of maximal volume. All right. So we got our N hypersphere. Ooh, that's a fancy word. What does that mean? There, we're going to claim in 4 dimensions. Then again, we are playing with 5 dimensions, so maybe we're doing an n minus 1 type of thing for a general expression. Again, don't know. We're conjecturing here. We can play. Let's have some fun. Because take out our general calculation here, because we're going to draw some stuff. We're going to draw kind of like the other day. And again, this is the first time I'm actually doing this, but we're going to play off. We're going to play through it. We're going to see where we go. Okay. We're going to draw our cone-like structure. We're going to go right through the center point's nose here. We're going to do our little yay, wee, all the way around. Yeah. We're just going that, blah, blah, blah. Okay. We got our cone going the other way. Wee, all the way around. Yay. Okay, so we got a cone. What seems to be doing stuff like that? Well, at least within physics and stuff. 1, get a light going. Number 2, well, we're interpreting this as this charge. Because if you run these out to a limit, basically going to loop back around and it's going to net itself out. So we're going to kind of like net things out there. Okay. I went through this per chart. I'm sure I'm slaughtering that. All I know is I watched, I think it was a Richard Dale video or something. And he literally just through mathematics and even mathematics, and I was able to like start following. I'm like, all right, with a combination of Wolfram Alpha and Chat GPT with Wolfram plugins and stuff, I'm pretty sure I could replicate what you just did there, especially referencing your video. Basically, if you just do the math, you get U1, aka the electromagnetic field, for free. Any sufficiently advanced technology is indistinguishable from magic. It's a quote from Arthur C. Clarke. Hey, Mark, what are we working on here? We're going to go with stuff and things. Some people may say, oh, you're trying to interpret everything. Is it everything? I'm just saying around the persistence. We're conjecturing what might be going on. Okay. So we've got our cone. It's charged. Oh, it's doing that twisty electromagnetic thing. All right. You get a cylinder, you kind of twist it. All right, I can kind of see that. It becomes like a conical structure. All right. Where do we go from here? All right. So we've got charge. Well, we're gonna need. Ooh, this is getting interesting. I'm forgetting my. Oh yeah, our hyperboloids. So we got our single sheeted pergola. So it's basically just gonna come around. It's gonna be like almost like, I don't know. It seems almost like a skin there. I believe we're claiming. Okay, that was. Some of these have changed. All I know is we come down to here. We get the two-sheeted one. We go over there. You go up to there. Basically, I think again it was in one of Richard's videos. We did have a gap here, and the claim is that was a mass gap. So we're considering this as mass. Okay, why? Now that's very interesting about why it might be appearing as negative. Is it some form of other things going on there? Perhaps. Um, So I think we had this labeled as space time. Was the interesting thing because we never actually gave it a label. It literally just seemed to be the iteration of causality, perhaps frequency, maybe another way to actually look at it. I don't know. All right, so we can go this dude. We'll call that space. I could be completely wrong. All right, but it's basically it's going to encompass everything. Oh yeah, and this, yeah, we had this ginormous number from there to there. Uh, This guy's smiling little radius is about 10 to the minus 8. Redonkulously small meters. Yes. All right. What the ultimate claim is, reality itself is cinched together by the strongest minimal double covered knot that emits a hyperbolic projection. Or at least everywhere where the knot is, you would have that projection. So there's actually the complement of the figure eight knot, which actually is a torus. And when the torus is inverted, it actually is claimed to become a hypersphere. First heard that from John Williamson, God rest his soul. But and there actually is some literature. I still need to go through a lot more literature, but I'm like, and worked for CERN for like 7 years, and you would bring up some things. You'd be like, there seem to be some anomalies in this data. And again, this is according to him, and other folks would need to verify this, but occasionally I think his biggest gripe was it's the anomalies. And then like a day or so later, it's like, what, these anomalies are gone. Well, yeah, we adjusted the model a little bit. It's like, um, are we just tweaking these things to kind of just like fit what we want, or did we notice these different things in science? And that actually brings up something that Wolfram was on earlier, and we got to talking a little bit about um, how certain things are in the literature and how some things are not in the literature. Quick example. And one of the reasons why I love listening to Wolfram's things is because he actually worked within particle physics. Like he actually like has been a scientist that has at least known scientists or has had real world interactions. And at some point he was talking about like some superfluidity experiment with I think it was like helium 3 or whatever. And basically they set up this experiment. And it's like the way it was set up, it's like, all right, there's no way you're able to replicate the exact same result. It's going to be completely random every time. And apparently, they set up the experiment very precisely well. And they showed a particular phenomenon that it's like, it seemed to do the exact same thing. And from what I remember, Wolfer's comments about the scientists were like, well, we have observed this thing. We don't know why it's happening. We haven't published because we were afraid people would make fun of us. So I sit back and I'm like, wait, hold on. You noticed something so spectacular. We have no idea, and it was reproducible. You have no idea how this happened, but you didn't publish, not because you're like, oh, no, the scientific method was all right. You were afraid of being made fun of. Now, apparently, I think this was like years ago. And you sit back and you're like, if this was years ago, I'm sure the internet and social media hasn't added additional pressures that may keep good scientists that are doing good work, that maybe there are some inconvenient results. But isn't that why you publish? Because if the results are wrong, if they're garbage results, then we're going to see it's garbage results. I mean, hey, I was cautiously optimistic. Okay, I was very optimistic about LK99. I totally wanted it to be. I looked at it. It came up with some. Oh, look at these things here. I have no idea. I'm not a chemist, but it's fun, and especially we got to see. Some folks would say that's there was a lot of drama, and apparently, I think some folks got in trouble for a lot of that jazz at some point. But ultimately, a lot of folks started to reproduce it. You're like, all right, we're seeing this effect. We have no idea what you're talking about. These superconducting effects. Some of these graphs don't even really necessarily seem to make sense. Uh, so if there's fraud, you're probably going to, or if somebody was quite wrong and made claims, basically, if they were writing claims from their mouth and their paper that their butts couldn't cash, usually doesn't work out too well. But had it been, if it was an actual thing, it would have been revolutionary. Um, where was I going over about that thing? Ah, yes, the technology and what we could actually get. Oh, yeah. We forgot our other friend here. All right. So, time, the inexorable continuation of reality, whatever that might mean. I'm going to go with probably the ticks of the Planck frequency clock. That's probably my best guess right there. Oh, yeah, because the inverse of the Planck time is Planck frequency. I know inversions are fantastic. Not always, but all right. Time, space, charge, mass. All right. Then we're going to need ginormous donut. Basically, a toroid, if you would, over here. Big donut. Num, 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 num. Yes. All right. And what is that? Our friend, TEMB, temperature. It's kind of like we're in the realm and where we live. Why? What is temperature? By more or less, it's the definition of vibration or the oscillation of different atomic stuff and things. Because why? Oh, it starts jittering. Well, it's gaining some energy. It's got to move some photons around, and things start to glow, and then they start to emit light. And apparently, when it becomes an ambient temperature with the environment around it and everything, it becomes a black body. What is a black body? Something that glows at a generalized temperature about that. Well, that doesn't necessarily seem black to me. I mean, that there is a temperature and everything, but it's the point where basically, if it's the temperature of everything else that is of that area enclosed, if you put it into a box and everything's basically kind of that stuff is going to glow at the same temperature. Okay. So that seems to be where we live. And again, this is great. Oh God, kind of looks like a basketball, maybe a weird circular football there. Oh, it kind of looked like a weird neuron. I apologize to all my little facey people and stuff. Okay. So what does this have to do with anything else I was saying? Okay. Here's what we're gonna do. We're gonna erase all the stuff. Why? Because I need room, and even that was confusing me. So don't feel worried. Kind of hashing things out as we go. Why? Well, that's why we're here. We learn. You teach me, and I'll teach you. The following word to that phrase is actually usually Pokemon. I I think if you ask ChatGPT to fill in the next little bit, it might actually do that because hey, It was good enough for Herman Cain to use in a speech, God rest his soul, then hey, I can totally rip off some Pokemon lyrics. All right. As I dropped the word Pokemon several times, it's the algorithm may for some reason recommend more folks come in. It's like, hey, I came here for Squirtle. What is this guy drawing random things on the board? Okay. So the claim is, how did we get here? Okay. Number one, first off, I don't know. I wasn't there. Only level 40. Haven't had enough time to parse through the other stuff. Well, hey, upcycle. Well, infinite space. Now, infinities are fascinating because number one, there are different types of infinities. And what are we defining as infinite? Because there are some things where it looks like, okay, it might be gimungulous, but it might be finite. I.e., you could probably eventually you could put the number on a computer at some point, something like that. Okay, but okay, I'm gonna need my ritual caffeine. All right, does Sprite even have caffeine? That's all right. I'll light it. Something has sugar. All right, so I can't get something from nothing. I'm sorry if that's what you're here for. I apologize. Um, need at least a void of, let's just say, random wave, just random. This is the point where we basically invoke the Roolead. All right, we exist in a realm, all possible rules, every different thing's going to happen at some point or another. At some point, you get a specific kit configuration. What's that configuration? We're going to call that the hyperbolic figure eight knot. We're going to do this. I'm just going to write H F 8, mostly because I can't draw it, or at least consistently yet. Um, it's actually going to be the complement. So it's HF8C. Why? Because you got the knot itself, and the unique thing about the figure eight knot is, okay, within knots you have the unknot, which is just a circle. Okay, it's just string attached to itself. All right. Then you have a lot of people's favorite, a trefoil. It's the simplest knot that has a crossing. And then you go up one more level to the figure eight. And then, I believe it was Thurston that first figured this out. He found that it actually, if you went through all the articulations of it, everywhere that the knot ended up not being would actually be that it would project a torus. So basically, you end up having this thingy here, and then just kind of goes down, loops around, loops back around, and there we go. We have a nice little figure eight thing here. I actually have a little prop we could use. Probably actually makes things easier. Let's we got this non-broken one and the broken one. Okay. No, I'm kind of glued it back together. All right. We get these guys here. So what's this guy here? All right. So the claim is this little, so that little thing is basically a little knot in the center. We got these cut out so you can kind of see. It's probably are these guys. Yeah, so you can kind of see it's going looping around in there. And then this can basically be put at any limit for its actual projection here. This is, I think, the base one that Henry Segerman et al. Had. You can order these from his website or just take the code and just print it out yourself. It's got like 250 million points or something in it. But basically, this is a toroid boundary. So the claim is this thing in the center. Now, to be fair, that actually covers it quite well. So I got this thing in the center. I'm going to claim, just for orientation purposes, it's going like this. Why? Because if this starts to generate rotation, and it starts to generate rotation, we're basically adding, if we assume fluid dynamics, yada, yada, and again, I'm not a professionally trained, like thermodynamist, scientist, physicist, yada, yada, whatever the proper term is. I'm not even a plumber. I've done minor plumbing. I never said I was a good plumber. Occasionally I have leaks. But the thing is, if this is spinning around, it might start to suck things in. It might go along this little, I don't know, kind of like if this was an apple, a worm would be eating its way through there. Let's call it a wormhole, shall we? Why? This might be where it actually comes in our reality, for better or worse. Okay, so if you got this thing spinning around the center here, okay. Now, before we get there, so ultimately the claim was you got like some void, random waves, random waves. Eventually, they're going to take a geometric form. That form there, this thing is going to start to come together. And again, this is pure speculation. All that energy, all those waves are going to now start to come in. Why? Well, you've just taken a form. Perhaps gravity comes into play, or just the fact that you actually have a stable, persistent form. At that point, you bring together all those waves, all the energy in that void collapses down, or at least X amount of energy collapses down, and then that toroidal component gets under so much intense pressure, or maybe we're in a higher dimension at this point. Maybe we're in the fifth dimension or in the fourth dimension. Maybe it doesn't matter. You just go through each other and then you extend out and balance out this minimal, excuse me, this minimal volume, double covered, orthogonally bound, I believe is an appropriate term. It might not be manifold that persists, that is basically the volume initially of two idealized tetrahedra. I know, two of the minimal platonic solid. I mean, hey, go figure there. Hyperbolic tetrahedra. If that all of a sudden projects out into a hypersphere, now, or to actually get to that hypersphere of that ginormous size, now I can see some expansion. Is it inflation? I don't know, but we're going to conjecture a couple of things right now from a little fantastical friend calculation here. So, coincidentally, you have different Planck constants, and some of the lesser known ones. Uh, let's go over here. All right, so we have one. Let's do the Planck pressure. Planck pressure, what is that? Okay. Oh, that's defined as a speed of light to the seventh over the gravitational constant squared times h bar. Okay. Well, it's like 10 to the 113 pascals. That is a ginormous number. Okay. So that's where kind of, what is it? When they're doing the vacuum energy density calculations, and it's like, all right, it should be, uh, that's why you get the, oh, some people say it's 120 orders of magnitude off. Because right now it's normally about 10 to the negative, what is it, 27 kilograms per cubic meter. So it's 5 times 10 to the negative 10 joules approximately. I think it's like 3, 5. Yeah, I have a video on it. Feel free to check it out. So we have the Planck pressure. Okay. So then we have something called the Planck density. And again, some of these things, it's like I have no idea why these numbers where they are. I'm like, where would they fit in? If we're going to claim that our five base Planck constants, time, space, charge, mass, and temperature, if we're going to claim that those are like primal bases for reality, well, these other bases should come in at some point or another, like mass density. So it's the same thing except it's C5. Speed of light to the fifth divided by big G squared times h bar. What is it? 10 to the 96 kilograms per cubic meter. That's dense as all heck, my dudes. But okay, I had no idea where that would come in. All right, how about this? Let's take the mass of observable universe divided by the Planck density. Should give us a length scale. Okay, what is that? 3 times 10 to the negative 44 cubic meters. It's really small. What is that on a length scale? Giving us meters cubed, so we gotta take it to the 1/3 of the cubic root. That's the magical stuff I'm typing in there. Okay. All right. So about 3 femtometers. All right. So we're right about the classical electron radius. That's really dang small. Okay. So that's where I think we get the idea of a primeval atom. Why? Because we're getting something that's entering the realm of, well, at least right around the magnitude of the classical electron radius, 10 to the minus 15 meters. Okay. So that's pretty dang small. All right. So there's an interesting thing that happens if, hold on, which guy is it? Okay, you're gonna have to take my word for it. But basically, if you take a radius of that and you apply the Planck force to it and everything, basically you get out a mass of basically this magnitude. It's gonna be, excuse me, 8.331 times 10 to the 61 kilograms. What is that? As we had before, we're about 8 orders of magnitude greater than the mass of ordinary matter in the universe. Okay. If you include the dark matter, it's about 7 orders of magnitude. Oh, doesn't that sound a little familiar, my friends? Okay, so total mass energy equivalent, about 10 to the 78 joules. Okay. So where does this number come in? So here's a fun thing. If let's do this by divide this term by the Planck mass. That's what we're playing with, right? Okay. Oh, excuse me. Density. Even though that might be an interesting thing. Okay. What do we get here? All right. Here's where the punchline is. We get 1.616 times 10 to the minus 35 meters cubed. Now, for those of you that have never seen that string of digits or exponential power, don't worry. We're here for you. What is that? So, coincidentally, that's of a very particular magnitude in the form of meters cubed. We happen to go to our good old friend, the Planck length. Planck length is 1.616 times 10 to the minus 35 meters. 1.16 times 10 to the minus 35 meters cubed, you say? Why is it that for that particular mass level, when divided by the Planck density, that ginormous number there, we happen to get an old friend with two additional additional directions of measure. I think that's a pretty neat thing, but we want to be accurate. So we actually need to compare. Let's do like we did before with our standard observational stuff. You know, you take the 1/3 root of the cubic root of it to get it down to a single length. All right. 2.5 times 10 to the negative 12 meters. All right. 2.5 picometers. All right. About the 3 times the distance of between atomic nuclei and a white dwarf. That's pretty compact. Oh, look. That was the debate about the electron's Compton wavelength. Now, it's not precisely. It's 2.52. It's 2.42. I haven't found a really beautiful thing that I can say with huge amounts of accuracy to factor that it would be equivalent to, but it's just very interesting that it happens to be about the electron's Compton wavelength right there. So that's actually about 3 orders of magnitude larger because we were at the negative 15 before. Let's go back. They were at minus 44, so that's. Oh, that's interesting. 12 times the volume of a what? Oh, that's cool. I've never seen that before. Groovy. The same one of this or this other dude. Comparisons is volume. Oh, oh, that's really neat. Hey, X. Uh, yeah, the speed of light. I think they go up to about the eighth and stuff. I think the maximum number of things that you'll find is hold on, I think it's Planck intensity. Yes, speed of light raised to the eighth power, divided by the gravitational constant squared times h bar, the elementary unit of action. What does it be? It's like 122 watts per square meter. My friends, you're gonna need a little bit more than sunglasses for that one. God, you might need. I don't even know if adamantium and vibranium would help you. I think you just get flashed out of existence. Ooh. Okay, so happier thoughts. Um, at least for the moment. Okay, so that's a very interesting thing. All right, so that's the claim, and or at least for that. Hold on. Okay, we don't need to scare with the mass anymore because we're trying to tell a story. All right. So ultimately, is what we're gonna do. We're gonna take the letters off. We're gonna have this little thing. All right. So as we bring in and we're condensing all those waves and everything. And I think Jen basically kind of described this to me. Like, all right, you've got all these waves coming in. Shout out to Jen from the Church of Entropy. And it's going to collapse together because it's following this probably this version. Ah, it's so pretty. Yay. But basically, it's this. Let me show the other one. Got some more contrast. And so we've got this. This is rotating. It takes form. All those random waves or whatever are going to be brought in. You're going to have all this energy. It's going to be coming in. It's going to invert. It's going to have an inversion, an outward project a hypersphere. But before that, it's basically probably, at least according to that calculation there, uh, yeah, going to be at about the Compton wavelength of an electron. Ridiculously small. And then it eventually gets about, we're claiming 10 to the minus 8 meters, and then about 10 to the 34 meters for our outside radii. All right. So you've got our little cosmic cinch here. All right, we got our figure eight knot there. Little loop. It's very tiny. All right. So this is 10 to the minus 8 meters. Okay. That guy. But a ginormous four-dimensional hypersphere, S3 if you would, gonna be 10 to the 34 meters. I know. Gimungulous. Now, what's going to happen during that time? All right, let's follow a lot of the standard model interpretation. All right, you're going to have that. Is inflation a thing? I have no idea, but what I'm thinking is you're going to have all that energy and everything. So at first, I'm like, all right, we're just going to have protons, neutrons, or positrons, electrons. We're going to have matter, antimatter. Is it annihilating what is going on? Now, my thought and conjecture I went through and I'm like, all right, we have like neutrinos, this or that. And I'm thinking, what is the simplest solution? And this is a very far out there conjecture. And that's why I'm saying I'm committing blasphemy on a whole bunch of levels. What's the simplest form of a thing we could have? When matter and antimatter come together, we get photons. But what if we let there be light? Like literally all that mass energy we were just talking about. What happens if, I don't know, maybe it was in another form? What form might that be? Let's go to our friend over here. So what if we did this? So what if we took that ginormous amount that we're claiming is the mass of our realm of persistence, our universe, so to speak? We multiply it by c squared. We get the mass energy equivalent. Okay. So what happens if we divide that by something else? Let's say Planck pressure. Oh, look, we got our good old friend that we had there before. So what if rather than thinking about it as just mass, we thought about it as mass energy? So what happens if you have a whole bunch of photons? You're under this ginormous pressure that's about, I don't know, the 10 to the 113 pascals. And it's going to try to go outward. As it goes outward, the pressure is going to decrease. And as it's decreasing, okay, here's the totally crazy part. Now, I mean I mean I'm just following logic and calculations right there. But what if, upon that field configuration we had before, this thing is spinning? So as this thing may start to expand out, take its form at a point of balance, this little thing's going and it's sucking up photons. And it's sucking up photons. They're kind of going around this way because remember, a photon can only go it can't go more than 90 degrees. But what happens if, I don't know, you were going really, really fast. It was really, really hot, and you're undergoing this high level articulation while you're going around over here and a Mobius twist and looping back around. And I don't know, you come out as a neutron or something. Hashtag neutron decay or whatever. Kali, shout out to Kali Fisher. Um, Quantum cyclic cosmology, she's calling it now, I believe. I mean, I just think I use the word eternal. Maybe hers is more accurate. Hey, history will say whatever you call whatever the best descriptive thing of the time is. Is it the best descriptive thing at the time at this moment? Probably not. But it's fun. We're going over a model. I'm getting some things out. I'm saying them for the first time because a lot of times you have things in your head, but if you're not able to actually communicate them, especially with other people, it's 12 is a beautiful number hex. That's the thing. And Jack's, I'm not an overly religious person, but every once in a while I conjecture God has a sense of humor. Okay, so we have this, but this thing is spinning again. Enormous amount of photons, pressure. So if this thing is spinning, and it's sucking in photons, and perhaps it's converting them. It's kind of, I don't know, maybe nodding them almost a little bit, if you would. I know, ancient ideas. Is that exactly what's happening? Yeah, I think it's a little bit more complicated than that, but extremely hot, dense realm of persistence, our colloquially called universe. It starts to expand, but this, converting it to matter, but that matter, it's still so hot that it doesn't really have a form. So you're kind of putting some whirls in it. As we're expanding out, this thing is spinning around. And if anyone's ever spinned anything, you notice occasionally that will cause some more spinning. And if we had a superfluid, hyperfluid, whatever you want to call it, something with minimal, if any, viscosity, well, there's some spinning going on. Kind of like with a superfluid, I don't know. You spin Newton's bucket rather than it going up the sides like it normally does at a particular level. That superfluid helium, as you spin the bucket, what do you have? Start to get little vortices. Little vortices here, little vortices here, and they start to pop up all over the place. So, hypothetically speaking, we start from a very hot, dense state as we went through our little calculations. Anyone's feel free to go back and go through them. Um, we have this hot, dense state. We have almost an agitator, if you would, kind of like in a washing machine. It's kind of like spinning around, but it has a preferred direction. But as a preferred direction, we have some superfluidic type processes, quark, gluon, plasma, whatever this thing is doing here. If they start to turn around, well, we may have a slight preferred direction. Is there anything else within physics that has a preferred direction? Feel free to let us know in the comments below or in the chat, or those who are temporally watching in the future. Okay. Also, if we were to have something like this and this maybe a little bit of a rotation gradient going on, and we get those little vortices or something, just a little something to relieve the angular momentum because there's some energy building up. I don't know. Might those be seeds for some of our early galactic friends? All these different galaxies and how many markers do I have in my pocket? Just one. The two others are over there. All right. So what happens if this thing is spinning and kind of creating some things? And okay, so we start to get stars. Yay, stars! And then the stars start to kind of galactic formations and stuff. Ooh, galaxies. Yay. All right. And then we start getting bigger galaxies. We start getting clusters and super clusters. Oh, wow. You got all these things kind of starting to form. And you're going to get black holes. They're going to be over here. And those black holes will get ginormous amounts of other stuff and things, and supermassive and potentially even hypermassive holes. So, but ultimately, the claim is all right, we're adding some gradient in here. We have a very hot quark gluon plasma, superfluidic type thing going on at a very high temperature. As it's expanding out, you're just going to have start to this angular momentum happening. You can have the seeds for stars, galaxies, whatever you want over there, or whatever would logically make sense when you actually do the computation. And I'm sure this will require a lot of supercomputer compute time, especially if we're saying it's orders of magnitude. Oh God, that's not negative. Wow, that was the inverse of the inverse. No, that wasn't the inverse. It would have been 35. But okay, but if that's happening, we start out the seeds of stars and galaxies. But if this has a direction, let's say this is going out. Well, that means this is accreting outwards. All right. Don't we need it to go inwards? So what would that mean? That would mean as we're going out here, and again, if we have some rotation gradient going on, if the mass is here and you got a bunch of mass over here, you got a bunch of mass over here a mass, there a mass, galaxy star, whatever have you here, we're going to have all these things. But if it's going to have some spin, if you would, let's say we go, which way? Oh, let's just go this way. All right. So if this thing is spinning, and I'm over here, I'm riding around, but there's other mass that's balancing me out over there. Doesn't that mean we're just going to kind of and as well as and then this stuff is going to oh my God, the universe recycles. Imagine my shock. Would be essentially the claim. Now, is this the way it is? I don't know. But at this point, oh God, the lines are going the wrong way. Lord save me. I'll probably be on saving. But at this point, it's like, wait a second. So what you're saying is stuff goes in, stuff comes out. Never a miscommunication. Always wanted to say that. But okay. So what are we getting? We're getting basically our realm or our observable universe as you would. But yeah, oh, is this big? Oh, maybe it's really old. Yeah, it's probably really old because I'm calling it OCDM, old cool dark matter. So let's bring ourselves all the way around to a point. Okay, what's the point? Well, the point is if we get to this point and we have all these stars and everything, and things are cycling back around, that means at some point maybe you're going to have black holes go in there. Now, are we going to get all the information out the way we want it? Probably not. Also, if black holes, if they're not actually fucking entropy radiationing faster than the actual amount of vacuum energy and stuff that's there, and do they ever effectively evaporate? I don't know. Maybe. But if at some point they get in here, I'm like, wait a second. Now, ultimately, the claim is it looks like a perpetual motion machine. If that's true, then it's eternal cyclic cosmology because barring outside interference, because what's out here? I don't know, dragons, maybe, argons. I don't know. Can only calculate up to here. Maybe it's like Men in Black. Maybe we're just some cosmic marble or something. I don't know. But if this was a perpetual motion machine, and motion machines are impossible with matter. What's the matter with matter? Because it can have, if you're trying to shield it from all the different field forces or actions, if you would, you would need to be perfectly opaque. Because in Stephen Wolfram's paper with Jean Amjo in 1981, they were doing something about the thermodynamics of the vacuum. And then a few years later, Robert Ford calls up Stephen Wolfram. He's like, "Are your calculations correct?" And Professor Wolf is like, "I'm pretty sure my calculations are correct." He's like, "Well, if your calculations are correct," he's like, "there must exist a configuration of a Carnot machine of like the second or third kind." And then Stephen Wolfram on the live stream, he just casually is like, "So I checked the calculations and he's right." And I'm like, wait. You said what? Basically, that's the whole where sounds like the concept of 0 point energy came from. And he just with a big smile, he's like, "Well, that may have not really made it into the realm of scientific fact. It definitely made it into science fiction." I'm like, wait. So that calculation that you did, that you could show some transform, so where you could essentially take energy out of the vacuum to perpetuate motion? What? Again, I don't think it's Robert Ford. Also happened to be a science fiction writer, so I feel like part of that idea really just made it into science fiction because of that. But he proposed some interesting things. Now, could you get them to work with ordinary matter? Stephen Wolfram, even himself, was like, "Yeah, probably not." He's like, "I suspect you could do it via field configuration." What are we conjecturing here, my friends? I don't know. That was why I did that whole crazy field configuration that was almost certainly wrong in multiple aspects earlier. Is that, wait a second. So if we're creating hot, dense states here, maybe for observers like us, we're about 13.8 billion or so years out here. At that point, we're literally just playing because, okay, maybe even if you black hole, now what happens when you inside out or invert a black hole? I have no idea. Maybe that's where literally the configuration or vacuum energy of space time itself is coming from. Perhaps it's just a simple thermodynamic flow of stuff and things. Maybe matter's being sucked in, it's coming out as antimatter. Maybe it's still sucking in photons because we still got a bunch of stars. If everything's gonna recycle at some point or another, I don't know. Not like the CMBs and about the temperature, the value of the base of natural logarithms, Euler's number. Euler. When you actually go into the gentleman saying his own name as of the house Euler, apparently we were all right until we became wrong. Okay. Arbitrary tangential diatribe aside, what's the whole claim? At some point, you have the hyperbolic figure 8 knots complement as a toroidal component out here being projected into the n hypersphere of maximal volume. It's approximately 8 orders of magnitude more mass, radius, standard parameterization. But if this is going out here now, wait a second. Now we have a method for dark energy. Why does things seem to be expanding? Maybe the universe is still expanding out. I don't know. What if we just had fluidity and increased pressure under pressure? And things just kind of spread out because isn't that what thermodynamics does? And again, wild speculation here at this point. But if it keeps going around, and if we've been around greater than 14 billion years, might that explain, especially with the other day, apparently there may be direct collapse from star to black hole things, maybe going about 30% of the time. Well, if those stars had planets and stuff, and they're just kind of swooping out of existence, or from our visible range within the ultraviolet and standard measures, um, yeah. What if there's a lot of old, cool, dark matter out there accounting for pretty much everything else? Oh yeah, and that when you take the that estimated value of mass for the universe, when you include visible matter and the dark matter, it's about 8 orders of magnitude different from our calculation there. So that calculation should include all the dark matter as well. Again, that's assuming Planck force is a relative useful thing one can use when computing. Shout out to Dr. Salvatore Pais and Rick DeWitt for that one. Rick had the confidence in the extra 8 pi. So, yeah, that's about all we got here. I've been ranting for an hour. So, Beetle, what's going on, my dude? Oh, dude, you're on X and that. Wow. Good to see you, my friend. Now we're just wrapping up. We're just trying to figure out how stuff and things might be going on. The blasphemy of tonight is basically we're conjecturing basically universe. If a perpetual motion machine were to exist, we might not be able to build it, but we might be inside it. And it looks like it might go on forever, and everything just kind of recycles itself. We're in like the most crazy, beautiful snow globe lava lamp you could think of. And then just have like a hyper pump in the center to just, like in a fish tank, just circulate everything around. There's more to it than that, but that's ultimately the gist of things. But hey, no, thank you everybody for who's tuning in now, who's tuned in for a few minutes, who accidentally clicked on this in the future. But that's all we got from now, and yeah, make my way back to the East Coast and see if we can't get some other stuff and things done. So, with that said, take care of yourselves, everyone, and happy holidays. Peace out, everybody.